Hello students, I welcome you all to this module 2, class 9 of electromagnetic waves video session. Myself Dr. Mahanteshke, Associate Professor of Department of Electronics and Communication Engineering, SJBIT Institute of Technology, Bangalore. So in this video, we will be discussing about the content of the entire module 2 and a couple of issues related to the Gauss law. The module 2 consists of Gauss law and divergence, energy potential and conductors. So let us see what do you mean by Gauss law and divergence at the first half of your module 2. So the results of Faraday's experiment with the concentric spheres could be concluded as an experimental law by stating that the electric flux passing through any imaginary surface lying between the two conducting sphere is equal to the charge enclosed within the imaginary surface, and that imaginary surface we call it as a Gaussian surface. Flux is equal to the total charge. Faraday's experiment can be generalized and also known as a Gauss law. So it states that the electric flux passing through any closed surface, here any means any irregular closed surface, including irregular closed surface, is equal to the total charge enclosed by that surface. So let us imagine a distribution of charge which is shown as a cloud of point charges here surrounded by a closed surface of any shape. The total charge is Q. So there will be a Q coulombs of electric flux which will pass through the enclosed surface. At every point on the surface, the electric flux density vector D will have some value of ds, and D must be evaluated at the surface. ds signifies the evaluation of D on the surface. So delta S defines an incremental element of area with a magnitude of delta S, and the direction is usually normal to the plane or tangential to the surface at any point of question. So at any point P where ds makes an angle theta with delta S, then the flux crossing through the small surface delta S is the product of the normal component of the ds and delta S. So this figure shows this is the electric flux and this would be the differential surface, and this is delta flux d psi and the flux crossing through delta S. So delta psi or ds is equal to flux crossing through the small delta S, which is given as ds cos theta into delta S, which is equal to ds dot delta S. So as it signifies the dot product, scalar dot product, so this appears to be as ds dot delta S. Therefore, this was the flux crossing through the delta S region. Now the total flux will be an integral of d psi or delta psi, which is equal to closed surface integral of d into ds. So the resultant integral, that is closed surface integral with respect to ds, always involves the differentials of two coordinates. So the integral is a double integral. We can formulate the Gauss law mathematically as psi is equal to dds, which is equal to the total charge enclosed within inside the same closed surface. The charge enclosed may be a point charge which will be the summation of all the point charges, or a line charge, which will be Q is equal to integral of rho L dl, and a surface charge Q is equal to rho S ds, or a volume charge which is equal to volume integral rho V dV. So we now take the general form of Gauss law can be written in terms of the volume charge distribution, that is closed surface integral dds is equal to volume integral rho V dV. So let us try to prove Gauss law using a point charge Q placed at the origin of a spherical coordinate system, and choose a closed surface ds at a radius a, and now the direction of d is normal to the surface ds. So the electric field intensity due to the point charge can be found as E is equal to Q by 4 pi epsilon naught r square in the direction AR. But we know the relationship between the flux density and the electric field intensity. It is epsilon naught times electric field intensity. Therefore, D is equal to Q by 4 pi r square in the direction AR. At the surface R equal to A, so replace R by A, so we are going to get flux density is equal to Q by 4 pi A square in the direction AR. But ds with respect to the spherical coordinate system in the direction AR is given by r square sine theta d theta d phi. So r is equal to A. Therefore, differential surface ds will be equal to A square sine theta d theta d phi in the direction AR. Now taking the dot product, that is dds is equal to Q by 4 pi A square into A square sine theta d phi AR dot AR, which is equal to 1. So the remaining variables are Q by 4 pi sine theta d phi. Therefore, psi is equal to dds, which can be written as double integral phi varying from 0 to 2 pi and theta varying from 0 to pi Q by 4 pi sine theta d phi, where r is equal to A. Solving this integral part, we are going to obtain the resultant value as Q. So therefore, the surface integral dds, which is equal to Q, which is equal to the total flux. So let us try to apply the Gauss law for some symmetrical charge distribution. Now consider how to use the Gauss law to calculate the electric field intensity. So we know, as per the Gauss law, Q is equal to closed surface integral dds. The solution is very easy if you are able to choose a closed surface which satisfies two conditions. The one, ds is everywhere, either normal or tangential, so that dds becomes either dds or 0 respectively. The second condition is, on that portion of the closed surface for which dds is not 0, therefore ds is constant. So for the point charge, the surface or the Gaussian surface which we are going to select would be a sphere. For the line charge, the surface will be a cylinder. From the previous discussion, we already tried to prove the application of Gauss law to the point charge. Now, we shall take from the previous discussion the uniform line charge, only the radial component of D is present. That means the flux density D will be equal to D rho in the direction A rho. So we have assumed a cylindrical Gaussian surface of length L, of radius rho, and the line charge density rho L. The choice of a surface is depending upon which fulfills the requirement or the two conditions, and we have selected a cylindrical surface. So d rho is very normal to the surface of a cylinder in the direction a rho. It may then be closed by two plane surfaces normal to the z-axis. So as per the Gauss law, Q is equal to surface integral, closed surface integral dds. But here d, closed surface integral, can be represented in three different sides. One with respect to the side of the cylinder, the second integral with respect to the top, and the third with respect to the bottom of the cylinder. As we have noticed in our previous discussion, electric field intensity or the flux density or the flux radiate outwards in the radial direction only. Hence, the flux densities with respect to the top and bottom surfaces tends to 0. The remaining coefficients will be in terms of the surface integral, closed surface integral with respect to the sides. So Q will be equal to d rho double integral, the first integral varying from z axis 0 to L, the second integral varying from 0 to 2 pi. This is an azimuthal angle rho d phi dz. Therefore, Q is equal to d rho 2 pi rho L. Therefore, d rho is equal to 2 pi Q by 2 pi by rho L or RL. We know that the charge enclosed is rho L into L. That is charge density into total length. Therefore, d rho is equal to rho L by 2 pi rho or 2 pi r. And since we know the equation, the relationship between the flux density and the electric field intensity, E can be equal to d rho divided by epsilon naught. Therefore, electric field intensity of infinite line charge will be equal to rho L over 2 pi epsilon naught r. So now let us just try to apply the Gauss law for some symmetrical charge distributions. The problem of a coaxial cable is almost identical to the application of Gauss law to the line charge. Let us consider a coaxial cable of two conducting cylinders, one with respect to an inner cylinder, solid cylinder, and the outer hollow cylinder of radius A and B respectively. Suppose that we have two coaxial cylindrical conductors, the inner of radius A and the outer of radius B, both with an infinite length. We shall assume a charge distribution of rho s on the outer surface of the inner conductor. Choosing a cylinder of length L and radius rho in such a way that A less than rho less than B as the Gaussian surface. So here we are going to assume a Gaussian surface here. Therefore, Q is equal to d 2 pi rho L. The total charge on the length of the inner conductor is Q is equal to 0 to L, 0 to 2 pi rho s A d phi dz, which is equal to 2 pi A L rho s. Therefore, ds is equal to A rho s by R. For 1 meter length, the inner conductor has 2 pi A rho s coulombs. Hence, rho L will be equal to 2 pi A rho s. Therefore, my previous equation becomes d is equal to rho L by 2 pi r in the direction AR. Every line of electric flux starting from the inner cylinder must terminate on the inner surface of the outer cylinder. Therefore, total charge on the outer cylinder will be is equal to minus 2 pi AL. Remember, it is minus 2 pi AL rho s due to inner cylinder. So this Q we have obtained previously. So this was obtained previously. Q is equal to, and now Q outer cylinder will be equal to minus 2 pi AL rho s of inner cylinder. Therefore, 2 pi BL, why? Because we have the outer radius as B. L rho s of outer cylinder is equal to minus 2 pi AL rho s of inner cylinder. Therefore, rho s outer cylinder is equal to minus A by B rho s of inner cylinder. If we use a cylinder of radius rho greater than B, then the total charge enclosed will be 0. So there is no electric field. ds is equal to 0. Due to simplicity, noise immunity and broad bandwidth coaxial cable is still the most common means of data transmission over short distances. Thank you guys. Hope you have enjoyed this video on Gauss law and applications of Gauss law to the point charge, line charge, and onto the coaxial cable. Thank you for watching this video. Take care.